Rajesh Gopakumar's interests are in theoretical physics, primarily at the intersection of quantum field theory and string theory. He would like to understand why string theory is a natural framework for describing a variety of phenomena. In particular, a lot of his research has focused on deciphering the ADS-CFT correspondence. Rajesh Gopakumar did his undergraduate degree in physics from IIT-Kanpur and went on to do his Ph.D. at Princeton University. After being a research associate at Harvard University, he moved to Harish-Chandra Research Institute in 2001 as associate professor and then professor. He was also a visiting long-term member at the Insitute for Advanced Study, Princeton, from 2001 to 2004. He is the recipient of the ICTP Prize in honor of GC Week in 2006, the Shanti Swarup Bhatnagar Award in 2009, the Swarna Jayanti Fellowship in 2006, the J.C. Bose Fellowship in 2015, the G.D. Birla Prize in 2013, and the TWAS Prize in the Physical Science in 2013. He is also a fellow of the Indian Academy of Sciences, the Indian National Science Academy and the National Academy of Sciences, India. He was elected Fellow of the World Academy of Sciences, that is TWAS, in 2015. He is a founding member of the Global Young Academy, that is GYA.
Okay, so good afternoon, everyone. So we are in Coherence 2021. So we know it has been 2 weeks since we started our journey in Coherence, organized by Physics from Kolkata, a community of students, individual and independent students who are trying to promote science with a noble social cause. We all know that these 2 years of pandemic, 2021 and the previous year, 2020, is a very extraordinary situation in the entire world. So in this situation, India also suffered a lot due to this pandemic and the COVID-19 outbreak. And in spite of this, our home state, West Bengal, suffered there is amount of two unexampled and annihilatory cyclones and etc. So there is a total extreme situation throughout the coastal areas of West Bengal. We all know that YAAS super cyclone and previous year's Amphan super cyclone totally destroyed the coastal regions of Sundarbans and etc. So in this context, we are going to create a new initiative called Rebuild Bengal. So we are trying to promoting science for the society with a motto and aim with that science with solidarity and science for society. We all know that science is not different from society. It is a key element of the society to develop, key element of our society for development. So that's why we are trying to do something which is called Rebuild Bengal. It is not only to promoting science, but also stand in solidarity with science and promoting the cause also. So now the very much idea of coherence, we all know this is a very popular phenomena for our quantum physics also. So we are trying to do something like to know about to extend the idea of very much idea of coherence into the society, and we are calling it coherence, the harmony of excellence. So this is our this is the second last day of our second phase of coherence. So we have Professor Rajesh Gopakumar with us in this afternoon. So I think we should invite him. Soham, can you hear me?
Hello. Yeah.
Hello.
Yeah. Thank you.
Welcome,
sir. Thank you very much for welcoming me to your event, and I'm very happy to support your very noble cause and to support this activity that you are taking out of your own initiative. I think it is it's very nice to see young people motivated by a sense of idealism towards society. And I wish you all the best in your goal of rebuilding Bengal and bringing aid to the people affected by COVID and YAAS.
Yeah. Actually, we are thinking that this is the high time to stand by the society because we know that our entire society is in very much crisis. So that's why we're thinking to do something like that. So
Yes.
if you have any specific opinion on our initiative, so you can share us.
No, from what I have seen outfit, I think it is very good that you have even taken a step in this direction, and you're fundraising for the cause. I think the coming few years will be very difficult for people in many sections of society, and people like us are relatively more privileged, and I think it is our societal responsibility to help the people who are bearing the brunt of this terrible pandemic and all the other calamities. So as I said, I wish the initiative all the best, and thank you for joining in for the talk today. Shall I share my screen? I mean, my screen is visible, or yeah.
Yes, sir. Visible, no,
Oh,
we are just adding it. So,
sure.
sir, I want to share one thing, a little thing that we all know that fundraising or donating is not only the solution. So, we are also trying to initiate this issue more further times. So, we can organize some kind of nature camps, etc., and the scientific cause behind these cyclones and etc. So, we are have a lots of plan, and we need supports from the genius minds and the famous minds from like you. So, thank you very much, and let's start the lecture. Everyone is waiting, so let's go for it. Thank you, sir.
Okay.
So,
Yeah.
your
So
video?
is it now full screen?
Yes, sir.
Can yeah. The
You are
so
visible, and your screen is also visible, sir.
visible, yeah, because it
Okay.
has become full screen on my laptop, so I can't make out. But let me know if there's any problem with the audio or the video.
Yes, sir. We
So
all are in the wings. If there is any kind of problem, we will notify you.
yeah.
Thank you. Let's start,
So,
sir.
so as I said, I will. I'm happy to be in this event of coherence, and I will talk about a certain quest. And in some ways, I think all of you, those of you who are here, many of you who are students and others, are on a quest. Especially physics is about a quest for learning more about the universe and kind of deciphering its underlying patterns. And I will talk about one such quest over here, which is something I find very fascinating. And so I will talk about this quest for quantum space-time. So I will explain as I go along and give a little glimpse of what it is. So like I like to say that it's like showing some pictures from a trek. If some of your friends have gone for a trek to the Himalayas and they come back and show you some panoramic pictures like this, that inspires you to perhaps one day make the trip yourself and see this glorious vistas. So this similarly, my talk is a kind of invitation for people to try to. Some of you may want to, after seeing some of the ideas, may want to participate in such a trek yourself. But even though I will focus on one particular aspect of physics and one particular quest of quantum spacetime, I think in all areas of physics, whatever you might be choosing to do, you will find there are very worthwhile and very fascinating quests, and all of you can make a contribution in that quest, because physics has arisen from a collective endeavor of thousands of people over the centuries. So that's something I feel is very noble thing to devote one's life to. So I started with this Himalayan metaphor. So let me say, continue on that for a little while. So all of you know that Kanchenjunga in the east is one of the highest peaks of the Himalayas. But very far away on the other end of the Himalayas is K2. And of course, Everest is somewhere in the middle. And so you have, this is several, the Kanchenjunga and K2 are several thousands of kilometers apart. So at some point in history, people did not realize that they are actually part of a single mountain range. But this is something, in a way, explorers had to very painstakingly go and map this and this is a picture of an early map of the Himalayas, and slowly they had to kind of chart out this territory, and that's how people realized that K2, which is somewhere over here, and Kanchenjunga over here, are part of the same several thousand kilometer long mountain range. So of course, nowadays you don't need even you can sit in your armchair and open Google Earth and see the connected mountain range from satellite pictures and see that again Kanchenjunga over here and K2 over here are part of the same range. So why I wanted to make this metaphor will become sort of clear soon. But let me start by saying about some things about the laws of physics in general. So what are the laws of physics? They actually are a way to they kind of collect the regularities that we see amidst all the complex behavior around us. We kind of pull out certain regular patterns and manage to understand these regularities amidst all very complex and often very chaotic behavior. And so the endeavor in physics and has been to capture this in precise mathematical language. And this is what I think people earlier did not realize, that some of these patterns in that you see around you can be captured in mathematical language and therefore measured and verified. And this is the power of physics. And remarkably enough, even as we have widened the scope of our laws, initially the laws were about things you see around you in your field of experience. You do some simple experiments like dropping a ball or throwing a rocket, launching a rocket, or looking at the behavior, how water flows, and so on. And you derive some simple laws about them. But gradually, physics has widened the scope of these laws, and we will discuss this, to a very large, to kind of encompass the very, very small and the very, very large, as well as the very, very complex. And as we have done that, we have been able to capture the regularities in mathematical language, even though there was no real, nothing really guaranteed that. But nevertheless, we have been able to do it. But sometimes, as we have widened the scope of the laws, we have had to have some conceptual as well as mathematical reorientation. And I will give examples of this. So this is why, so let me come back to our understanding in physics. What people have done is a bit like what I started out by saying about the charting of the maps on Earth. You have what people did were they discovered simple laws, maybe Archimedes' law or some Pascal's law, and then Newton's law of motion, and so on. And you you did, so to say, a ground survey, and looked at things around you and discovered these simple laws. But gradually you pieced these laws together and tried to make more general laws. That's a bit like seeing all the different peaks. So I want to think of each of the laws that you learn as sort of peaks in our understanding of nature, and but you are putting together many of these peaks and trying to see a range appear, and that by broadening that scope, you see the connectedness between all the different peaks, and they kind of become and once you see that, you can actually see the vista of the whole Himalayas. And that's how it has been in physics. In fact, there are two peaks of 20th century physics, which you have all probably heard of. And these are what are called the general theory of relativity, or general relativity for short, and quantum field theory, or QFT for short. These have been the main pillars of 20th century theoretical physics, because general relativity, or GTR, has given us a successful theory of the cosmos and its evolution on the very largest scales, on the extremely large, and how large I will say in a moment. Whereas quantum field theory has captured the physics at the smallest length scales that we can probe. So these are two different peaks. One is about the very largest, and one is about the very smallest. And today's story is about how we are beginning to see this connectedness between these two peaks, which seem to be very far apart, somewhat like Kanchenjunga and K2, seem to have nothing to do with each other. But we'll see that we are beginning to understand the connectedness between these two peaks of 20th century. So let me start with gravity, this topic of the general theory of relativity, but step back even earlier. So gravity is the most common force in nature. It is something we all feel. We all are subject to gravity all the time, and we feel the effects of neglecting gravity when you fall down or break a bone. So this was, in some sense, the force that also was understood first in a very universal sense, and that was accomplished by Newton, who put forth the Newton's law of gravitation, which you have all studied in high school or BSc, which states that the gravitational force between two bodies of masses m1 and m2 is inversely proportional to the distance r square, and there's a constant of proportionality, the Newton's constant of gravitation, which is a universal constant, and times this force vector is pointing in the is an attractive force in the radial direction between the two bodies. So this is universal in the sense, and that was in a sense the big leap of Isaac Newton. He was saying that it applies equally well for not only for the apple falling to the earth, but also the motion of planets and things like Mangalyaan or Chandrayaan, or all the satellites that we send to various to outer space. They're all captured by the same universal law, which is quite remarkable if you think about it. However, it was not realized in Newton's time, but we have now realized that Newton's law, like all physical laws, actually has a certain range of validity. This law can be applied only as long as some conditions are satisfied. And if they are not satisfied, Newton's law breaks down. So when does it break down? I don't know if this is not something which is often taught in schools, but I feel it should be, that Newton's law breaks down under two different sets of extreme circumstances. And what are these two sets of extreme circumstances? So these are when the first is when objects move very fast. And very fast, I mean things which are velocities which are comparable to the speed of light, 300,000 kilometers per second. There are objects in the universe which rotate at relativistic velocities, whose and motion like this is an artist's conception of a pulsar, which is rotating at a large fraction of the speed of light and sends out jets of radiation as well as matter, which are also relativistic. So this is one set of circumstances where Newton's law breaks down, when objects are relativistic. Of course, in our solar system, we don't see too many objects moving relativistically. So that's why we never had in Newton's time, and for a couple of centuries afterwards, we did not realize this limitation. The other limitation comes when the density becomes very large. So example, at the centers of galaxies like this one, and we now know, and maybe you have seen pictures that are recent times, people have tried to image, there are these black holes, which I will come to, at the centers of galaxies, which come because of the collapse of very heavy stars, cumulatively forming gigantic black holes. So just keep this in mind, that Newton's laws do not apply when things are moving either very fast or when the density becomes very large. So how do you overcome these limitations? And this is what Einstein taught us. And here is Einstein writing his most famous equation, which he realized enables you to go beyond Newtonian theory. And in fact, his description is applicable at arbitrarily high velocities, what are called relativistic velocities, comparable to the speed of light. It's also applicable for moderately high densities, like the ones that you see, for example, in neutron stars. And this is what is needed to describe the physics of fairly heavy stars that have formed after supernova have exploded. Einstein's theory succeeded, as I said, partially in overcoming the limitations of Newtonian gravity. But the point I want to convey is that he accomplished this not just by changing Newton's law a little bit, by adding one extra term, or by sort of just adjusting some parameters, making some incremental changes. It was a very revolutionary development, Einsteinian gravity, because he changed the whole framework which is used to describe gravity. He just very radically changed that framework. And what he replaced the Newton's law of gravity was by a more sophisticated mathematical description in terms of the geometry of space and time itself. So this was very radical, because till then, and even intuitively, we all think of space and time as some kind of a passive stage on which all the events of our life and of all physical events, everything occurs at some point in space, some point in time, and that's space and time itself are some kind of passive stage. Just like on a drama, you have the backdrop. That backdrop is just a backdrop. But what Einstein said is that space and time are dynamical. Dynamical means that they are actively participating in the physical events, in the dynamical evolution of the universe. And in particular, the space-time responds to the contents, to the energy and the momentum of the objects which are in the space-time, and in fact of the energy and the space-time itself, that the space-time itself can carry. So this was very remarkable sort of a leap, and changed the way in which you sort of viewed space-time. And this is a cartoon picture. It's only very accurate, very kind of very basic caricature of the way space-time geometry gets affected by objects moving in it. So instead of the Newton's law in which the satellite was going around the Earth because of the inverse square law of attraction, the Einstein's picture is that the Earth curves the space-time around it in a way which is sort of pictured here, as if like here it's something like a two-dimensional part of the space-time that they are showing as curved, because we cannot visualize curved space-times higher than 2 dimensions. So this two-dimensional space-time is kind of curved, and because of that curvature, like in a rubber mat, when you curve it, the objects moving in that curved space-time will move not in the usual straight lines, but in a more curved geodesics, what are called geodesics, or paths of the shortest paths on these curved spacetimes. So that's the picture that Einstein replaced Newton's laws with. So, as I said, this was a conceptual, as I said, when you expand the scope of your laws, very often you have to change the conceptual framework, and that is what I tried to explain for gravity and Newton's and Einstein's rethinking of gravity. But mathematically also you have to change the framework, and that's what Einstein's theory it is not just a picture, it is precise mathematical equations, and these equations are very different from Newton's equations, and they are given in terms of this mathematical object called the metric that had been introduced by mathematicians like Riemann about just 50 years before Einstein's discovery, as a way to describe more general geometries. And this metric is you can view it, think of it in many ways. If you are a physicist, you can view it as a generalization of an electric field or a magnetic field, which are also fields in that they depend on position and time. Electric fields and magnetic fields are vectors. They have multiple components at each point in space and time. A metric is a more complicated object, which is like having a matrix at every point in space and time. So that's why there are two indices. It's like a matrix valued field, or a tensor field, as it is sometimes called. And this field measures, it can be used to compute the distances in this curved space-time. That's the fundamental role of the metric, is to show how the distances are different from those computed in a flat space-time. The flat space-time corresponds to when this matrix is just an identity matrix, so to say. And derivatives, because now this field can in general not be just a constant but depend on space and time. You can take derivatives of this field with respect to x or t, and those measure the second derivative of this appropriate second derivative measures the curvature, how much the space-time is curved. So it is in terms of this curvature of this metric that Einstein wrote down his equations. So they are, in a sense, partial differential equations, somewhat like Maxwell's equations, telling you how the metric, which is the analog of the electric magnetic field, as I said, how these are determined in terms of the matter and energy of that is there in the space-time. And quite remarkably, these equations reduced to Newton's laws at low densities and velocities. That is, in a sense, one of the most remarkable things about this theory, that I have started with something very far away, apparently, from the Newtonian description. But once I consider low densities and velocities, I recovered Newton's equation, Newton's law of gravity. So, which is what any good theory must. If you are trying to widen the scope of a theory and describe a larger set of circumstances, the minimal consistency requirement is that it should reduce to the previous theory, successful theory that you already have for the smaller range of circumstances. This is the consistency requirement which Einstein's theory satisfies very well. Sorry, there is a train. It'll just be a minute. So, general relativity, this theory of Einstein's, is now the picture of gravity that we have, which is very successful all the way to the largest scales of the universe that we have explored. And what is that scale? It is 1,000,000 times the size of the Milky Way. So the Milky Way, which is our galaxy, in which our solar system is a little small corner on the periphery, this Milky Way itself is just one tiny speck in this bigger universe that we have been able to explore. And as far as we know, Einstein's theory of general relativity describes the universe very well, essentially all the way through to these largest scales of the universe. So each of these are some galaxies, and there are millions of galaxies in the universe now. But now I want to introduce our second peak, the second actor in the story, which is the world of quantum mechanics. And quantum field theory, which I mentioned, was the second big pillar. And this is, in fact, it's quite remarkable that both these developments, the general relativity and quantum mechanics, happened within 10 years of each other, about a century ago. And what was realized is that when you go to very small distances, the reality has to be described by something quite different from the Newtonian description of laws of motion. What we learn in school is that F is equal to ma is the basic underlying equation for describing particle motion. But that's in terms of positions and velocities, which are the things you measure, and then you solve some differential equation, Newton's laws, to find out how particles move in time. But quantum mechanics gave a completely different picture, especially when it came to atoms, and this was very disturbing for many people, because it said that classical measurables like position, velocity, energy, angular momentum, these have statistical outcomes. So now, if you try to apply this philosophy of quantum mechanics to space-time itself, it's very puzzling, because now space-time we just discussed was being described by geometry. So how is geometry of space and time somehow a statistically averaged notion? How can you consistently describe that? And how can you talk of the so-called quantum fluctuations of the metric, which are responsible for these statistical outcomes? And so the question has been almost for a century of how to reconcile Einstein's picture with quantum mechanics. So this brings us to the limitations of Einstein's law, because Einstein's law, while it helped to enlarge the scope from Newton's law, I said that it only partially overcame some of the limitations, because there is so Einstein's description also breaks down if you push it to the extreme. And again, there are two sets of limiting circumstances where it breaks down. One is at very short distances, the so-called Planck distance. So the Planck distance is a distance which you can form from the basic constants of nature, like the Planck's constant, the Newton's constant, and the speed of light, and it works out to something like 10 to the minus 35 meters. And this, at these distances, we expect Einstein's description to break down. The idea of a continuous space-time to break down, just like Maxwell's equations broke down when we described atoms, when we went to the atomic scale. The other set of circumstances is when you go to ultra high densities. I said Einstein's theory was successful description at moderately high densities, like in neutron stars, but neutron stars are not the ultimately high densities we have in nature, even though they're considerably dense. I don't know if you know, but like a teaspoonful of neutron star matter weighs as much as the Earth. So it's incredibly dense. But you can go even beyond. And if you try to describe these situations in Einstein's theory, you find that the equations, the Einstein equations themselves exhibit a breakdown, and they develop what are called singularities. And this is one of the things that Hawking and Penrose, who got the Nobel Prize last year, are famous for, that they showed that Einstein's theory very naturally develops these infinities. So if you try to evolve the Einstein's equations, you find at some point that the equations, the solution becomes nonsensical. It develops an infinity, which is clearly unphysical. So this is why there is a need for a description that overcomes these limitations of Einstein's theory. And in other words, you need a quantum theory of gravity, a theory of gravity which incorporates quantum mechanics. So what are the circumstances where these might be important? You might think, oh, why should I bother? It is probably something very exotic. But it is something also very fundamental, because to understand the very birth of the physical universe as we now know it, or to understand this phenomenon of black holes, which I will say something about soon, you need to know about quantum mechanics, quantum theory of gravity. So I won't have very much to say about the quantum gravity in the context of cosmology or the universe, but just to show you this picture of how of what our current picture is for the expansion of the universe. From the time of the Big Bang, there was what is called a period of inflation, and then so on. We have a very good picture of how the stars form, the galaxies, planets, and now the accelerated universe that we see. But right at the beginning, there were these quantum fluctuations, which in fact seeded a lot of this structure in the universe that we see today. The universe is not homogeneous. It has a lot of inhomogeneities. And to understand that, we need to understand these quantum fluctuations fully. We need to have a full quantum theory of gravity. The other a place where it's very important is to understand black holes, which, as you have probably heard, in the last 5 years, we have had a dramatic increase in the way we have been able to detect black holes, namely through gravitational radiation, and also in the context of supermassive black holes in galaxies through radio imaging, quite incredible radio imaging. So we now realize that black holes are very common in the universe. They were at some point thought to be very exotic. So that's the place. These are places where, to understand really what is going on, you need to have a quantum theory of gravity, because as Hawking and Penrose showed, singularities are very are unavoidable when you are considering something like the Big Bang or black holes. So the way, so at first sight, you might think, what is the big deal about finding a theory of quantum gravity? Because somewhat analogous situation existed in electrodynamics. There's a superficially analogous situation, because Maxwell's laws, which you all have studied, give a very good classical description of electrodynamics, and that's what is the basis for all our electrical gadgets and so on, and that's very good. It is very accurate, but it breaks down. And where does it break down? It's very similar to the way Newton's law broke down. It breaks down at atomic scales, and we know that because electrons are in orbits around nucleus, and yet they do not radiate the way classical Maxwell's equations would have told you they do. But instead, there is a quantum theory of electrodynamics which tells you how to describe the electrons and their interactions with light and electromagnetism. There's another regime also of large electric and magnetic fields, like in lasers, etc., where also Maxwell's laws break down. But we now have a very successful quantum field theory, as it is called, namely the quantum electrodynamics of the electric and magnetic fields. A very successful theory, which is in fact one of the most precisely measured and verified theories. Up to something like 10 decimal places, it has been shown to be accurate. So you might think, why can't you study the gravitational field in a similar way? Because after all, I told you the metric field, this metric tensor, is just a sort of a small generalization, it seems, of the electric field or the magnetic field. But this is where our framework of understanding quantum field theory comes up with also its limitations, because various attempts that people have made to describe gravity in a quantum field theory also seem to fail. And though we don't have a clear understanding why, but there seems to be a limitation of quantum field theory in describing when we are considering the fluctuations of this geometry of space-time itself. Normally, when you consider quantum field theory, you assume that there is a fixed stage or a fixed backdrop, in my language of having a drama and a stage. The stage of space-time is normally taken to be fixed when you consider quantum field theories. But if you want to deal with the quantum field theory and its fluctuations, that seems to be something quantum field theory doesn't seem to be good at doing. So quantizing geometry or space-time is more subtle, and than it was for quantizing electrodynamics or electric and magnetic fields. And this failure of quantum field theory can be seen by the various puzzles that black holes have. So when you try to study black holes, and let me say again, many of you know this, that black holes are formed when there's a star which collapses because it is unable to withstand its gravitational pull. And in some sense, this goes back to the work of Subramaniam Chandrasekhar, that ultimately there is nothing that can withstand that, and there's no pressure inside that can withstand this gravitational pull. And in some sense, matter gets compressed to a super dense point, which is described by a very unique solution to Einstein's equations, the so-called Schwarzschild solution, or more generally what is called the Kerr solution, and so on. So these black holes are a very remarkable theoretical laboratory for studying quantum effects in gravity. So this is something I want to emphasize, that we still don't have a way to directly access experimental results, which direct experiments which can access quantum effects in gravity, except maybe in the early universe, maybe we can see signatures of that. So which is why black holes have been one of the most favorite theoretical laboratories, where you can try to understand, see how far you can understand the puzzles theoretically. And the work of Stephen Hawking played a very important role in this, because he realized that any quantum mechanical description of black holes will have to assign them a temperature and an entropy, which was something really radical, because at first sight you think, what does temperature and entropy have to do with an object like a black hole? And these are the famous Hawking formulas for the temperature of the simplest kind of black hole, what is called the Schwarzschild black hole. This H bar is the Planck's constant, G is the Newton's constant we had earlier, M is the mass of the black hole. And this is the so-called Bekenstein-Hawking entropy formula, which says that the entropy is equal to the area of the horizon of a black hole divided by 4 times the Planck's constant times g. Here I've set the new speed of light equals to 1, but you can put that back in. So the area of the horizon, by the way, I should say black holes have this radius called the Schwarzschild radius, beyond which light cannot escape, and that's called the horizon of the black hole. Light cannot escape to the outside world, and so in the simplest case, that radius gives a sphere whose area 4 pi r square that you take is what would appear over here. So, but fundamentally, this was very puzzling, this Hawking's discovery, because it suggests that black holes should have some internal structure, because after all, when do you assign entropy or temperature to a system? That is when it's a collection of a large number of so-called microstates or individual states, which give rise to an aggregate object. And so this is something very puzzling, because on the one hand, black holes seem to be unique solutions of Einstein's equations. Also, even then, there is a further puzzle, that the entropy is not proportional to the volume of the black hole, but it is proportional to the area of the black hole, the surface area, which it never happens for an extensive quantity in nature. When you have a box of gas molecules, its entropy is extensive. That is, entropy is an extensive thermodynamic quantity. It's proportional to the volume of the quantity of the system that you are studying. So in some sense, this is a hint that quantum gravity is very unlike a quantum field theory. In a quantum field theory, the entropy would have been extensive, proportional to the volume, but here it's proportional to the area. So the degrees of freedom in quantum gravity seem far fewer than they are in regular quantum field theory. So now let me bring in the last minutes of the talk the idea of string theory and what it has to say about these puzzles of gravity, and why we are beginning to see the connection between the quantum field theories and gravity. So in some ways, string theory's historical origin is from quantum field theory. It started as a kind of a modification of quantum field theory. I call it a conservatively radical modification, because it is a little bit of a major generalization, but at the same time, it doesn't really change the rules of quantum mechanics and so on. And what it describes is, instead of point-like particles as the basic constituents, you have these extended objects or strings, and you consider the quantum dynamics of these extended objects. When you consider the quantum mechanics of these extended objects, it's a very constrained framework. It cannot, you can't actually don't have that much freedom with the dynamics that you can have. In fact, it is much more so than in quantum field theory, which can come in a variety of different, there are many varieties of quantum field theories, but string theories are essentially unique. So this framework showed some very early promise in addressing some of the basic difficulties that quantum field theory had with respect to gravity, such as certain divergences that you would get if you naively tried to scatter gravitons of each other. The question of quantum, what is quantum space-time, was not something that was really properly addressed. And this is something that has begun to change in the last couple of decades, because from the internal consistency of the theory itself, there was a major surprising development which allowed one to make a precise proposal for the quantum behavior, at least for a large class of space-times. And the surprising answer was that in all these cases, quantum gravity is a quantum field theory in disguise. And why is it in disguise? It is because it is in some sense in one lower dimension than you might think. So let me try to explain this a little. And this is the proposal by the Argentinian physicist Juan Maldacena, and the kind of and the class of spacetimes that I mentioned in my previous slide are the so-called anti-de Sitter spacetimes, and this is a picture of an anti-de Sitter spacetime. It is a spacetime which has a constant negative curvature. And there are these paintings by this Dutch artist, Escher, which capture that the geometry of constant negatively curved spaces very nicely. It takes some getting used to this so-called hyperbolic geometry. It's in some ways the geometry you would have on a hyperboloid. And this is another way to represent that. And of course, here we are considering not just space, but space-time. And so there's a time direction as well. And you can think of, for instance, this can be viewed, the solid cylinder here can be viewed as a three-dimensional anti-de Sitter space-time, as a picture of a three-dimensional anti-de Sitter space-time, two space and one time direction. The statement of statement of Maldacena, the proposal was that this theory is dual to a quantum field theory now on the boundary of this anti-de Sitter space-time, which is like a cylinder, which is the cylinder that you see, the two-dimensional cylinder on the boundary. That's a two-dimensional space-time, and you can consider quantum field theory on that one lower dimensional space-time. And similarly, you can think of four-dimensional anti-de Sitter space-time, which will have a three-dimensional boundary. And the statement is that quantum field theory, quantum gravity in that four-dimensional space-time is equivalent to a quantum field theory, what is called a gauge theory, on the boundary of that space-time, the three-dimensional boundary. So this quantum field theory is not a quantization of the metric field of your original theory, but it is a quantization of a different set of fields. There are kind of gauge fields, generalizations of gauge fields in electromagnetism, and there is a precise dictionary between the bulk space-time quantities in that quantum gravity theory and the computations you can do on the boundary of that theory. So this picture has given rise to the notion that quantum gravity in some sense is holographic, because everything about this quantum ADS spacetime is encoded in the quantum field theory on the boundary. And this is very much like the idea of a hologram, a two-dimensional hologram capturing three-dimensional image. And this is some artist's depiction of that. So this is a very surprising picture that has come out of the investigations of string theory. And this tells us quite a bit about the physics of black holes, at least in this class of space-time. And you expect these lessons to be very general. And so what you find is that a black hole is indeed a state in the quantum field theory in the boundary, this so to say dual quantum field theory, which is at finite temperature. So the Hawking temperature is the temperature of that quantum field theory. It is like considering a system in one lower dimension at some finite temperature, and this gives the microscopic description of the entropy that contributes to the black hole. And you see also that the entropy is proportional to the area, which is like one lower dimensional, because it is extensive not in the original space-time, but it's extensive in terms of the boundary space-time, in terms of the quantum field theory on the boundary. So coming back to our original quest, what have we learned, or what are we learning? What we are learning is that quantum gravity is probably holographic in nature, and in some ways we can in some ways use that to understand this Bekenstein-Hawking entropy in a microscopic way. And more conceptually, I think we are having, like in the time of Einstein, a different conceptual revolution of understanding space and time itself as in some ways emergent in some classical limit. And they are not fundamental quantities, and there are some other basic quantities. It's a bit like considering water, which you think of as a very continuous, smooth flowing quantity, which doesn't seem to be something you can divide, but yet you know that underlying water are molecules or atoms, and the water that you see emerges, the continuous description of water that you describe by equations of fluid dynamics emerges only in a certain limit, in a classical limit. And perhaps it is like that with space-time as well, but we need to understand this better. We need to sort of decode this hologram more in a better way than we have so far. So this is why it is an ongoing quest. And besides, I told you this was in a class of space-times that we see this behavior. The question is this how quantum space-time behaves in all cases? So that these are questions we are trying to understand. So in the meanwhile, I think this connection has also already uncovered many striking facts about quantum field theories, which are strongly interacting. And even though, as I said, the study of quantum gravity by its nature is very difficult to have experimental evidence, but here the ideas of quantum gravity that are coming out of string theory in some sense are making theoretical predictions about theories which predate string theory, which were suggested over half a century before string theory was discovered. And these statements are falsifiable, and they have been verified. In fact, the predictions of these theories have been verified in a very non-trivial way over the last couple of decades. So I think this understanding this connection between this holographic connection between quantum field theories and quantum gravity is something that will give us new insights in both sides, both in quantum field theory as well as to quantum gravity. And it is potentially very powerful even in describing many real world things that quantum field theory describes. So I feel the 21st century will actually see these two different peaks of 20th century being linked together in a panorama. So I will leave you with just the picture of the Himalayas. Thank you very much.
So thank you, sir. Thanks for the wonderful talk. And there is several questions. Many of the participants raised some questions, and
Sure.
this is
I will be
uh,
happy to.
first of all
Okay, sir.
from.
First of all, sir, very much thank you for your talk.
Okay, so can I?
Let me introduce Seema Sarkar. She is our junior student. So I think, Seema, you can introduce yourself first.
Okay. So first of all, I am Shima Karmakar, BSc third year student from Calcutta University. So,
Nice.
sir, take
So,
it
okay,
to
sir, we have questions.
questions.
So Seema is asking the questions. And sir, for your kind information, the questions are also visible in the bottom.
Yeah,
You can see it also.
I can see that.
Yes.
Yeah.
Okay. Okay. So,
Yeah.
Seema, continue. I think I should wait on wings. Thank you very much, sir, for your
Okay.
talk.
Thank
Okay.
you.
Okay. Okay. So,
Yeah. So
first
the
question
first
is from Facebook
question.
Live,
Yeah.
and there is a Shrub Nata. He wants to know that, sir, my first question is it possible to understand the mysterious information of the multiverse and the infinite universe through string theory and the theory of everything?
Yeah, so the multiverse is an idea that has come, has been talked about by many physicists in the context of string theory, and the possibility that there are many different possible mm, uh, vacua, so to say, or solutions of string theory which correspond to universes in which the laws of nature might be slightly different, in which not the laws of nature, the different forces and their strengths might be slightly different, the parameters might be slightly different. And so string theory seems to predict that there, at least at the level we understand it now, it seems to predict that there are many possibilities, and that is the idea of the multiverse. But I think this is something we need to understand better. I don't think it is a settled question, or it is a very 100% firm prediction that the idea of multiverse is coming from string theory. So uh, we I think we'll have to understand the string theory better to make a definitive statement on that. The second question about the black hole and the wormhole. Yes, the idea is that many puzzles about black holes and can be solved using the ideas of quantum gravity, especially the ones that are coming from string theory. In particular, the idea wormholes are an idea that wormholes are a kind of a interesting solution of Einstein's theory, in which you can seem to connect two different parts of the universe by a kind of a tube or a wormhole. And some of these ideas have been recently proposed to understand the so-called information paradox of black holes, about if black holes are radiating with the Hawking temperature, what is the where is the information that went into the black hole, where is it gone? And these ideas of wormholes have made an appearance there, but I must stress that all these are ideas that are at the moment being churned. They are not. I mean, there are. I think that is how the process of research goes on. That you will be. People propose and others will criticize, and slowly you arrive at a correct idea of what is reliable and what is the right resolution, because very often when you first propose an idea, you don't have all the arguments for it, or you don't always see some of the weaknesses of the proposal. So most of these ideas that you mentioned, the multiverse, wormholes, they're very fascinating ideas, but they are still at the realm of speculation as of now. Yeah, so very good question. What is meant by quantum fluctuations of space-time? That is what one is. It is trying to answer that question that quantum gravity. This is the central question of quantum gravity. What do you mean, or how will you describe the quantum fluctuations of space-time? The picture that seems to be suggested, at least through the proposal that I described in my last few slides, is that space-time is not a fundamental object. There are more fundamental degrees of freedom, which at the microscopic level, maybe they will be visible only at the Planck level, at the level of Planck disk size. And these will be so space-time will emerge only in a certain limit out of these underlying atoms of space-time, could say. And you have to consider the fluctuations of these underlying degrees of freedom, and there will be eventually a continuum description in terms of space-time. This was the reason I mentioned this analogy with water, that water you describe by equations of fluid dynamics, in which you just describe the velocity field of water. But you know that ultimately water is made of atoms, and that is not something you see directly. But it is important for understanding the detailed properties of water. You need to know that it's made of molecules of certain kind. So similarly with space-time, we might be having a similar picture. That is what this Mulder-Senner's proposal, or what is called the ADS-CFT correspondence, or the gauge string duality. These are multiple names that are used for this proposal that I talked about in anti-de Sitter spacetime. And so this seems to suggest that sort of a that spacetime is not fundamental.
Okay, sir, I have a question.
Yeah.
Should I ask you?
Sure.
First of all, I have a question. You are speaking about the multiverse theory, so I don't know much about that. I think Leonard Susskind have a prediction on black holes and information theory, that he has a special phrase called EPR is equals to Einstein Podolsky and Rosen bridge equals to the Einstein Rosen bridge. EPR is equals to ER. So I want to know that how it can be defined, or why he is proposing such kind of things, and what kind of problems and what kind of advantage of that kind of hypothesis, or etc. So if you can elaborate about that EPR is equals to ER paradox.
Yeah, this is in the context not of the multiverse, but of the wormholes, because this Einstein-Rosen bridge is sort of the simplest example of a wormhole solution that was found by Einstein and Rosen long ago. It is coincidental that Einstein and Rosen, together with Podolsky almost in the same year or very shortly, also proposed something to do with quantum mechanics, which is called the EPR paradox, and has to do with the entanglement of quantum mechanical states. So what this ER is equal to EPR proposal is that whenever there is an entanglement between quantum mechanical states, in some sense, effectively, there is some kind of a wormhole between them. And that's what is important for preserving the... so entanglement kind of generates these wormholes, which are important for the for preserving the information that might otherwise be lost in the Hawking radiation. But again, like I said earlier, this is also at the moment just at the level of a speculation or an idea, and until it is really put on firm footing, we don't really know whether that's indeed correct or not. But it is an idea.
Okay, sorry. Seema, you can ask the next question.
Okay, so next question, actually two questions from my side, and their first question is, how can I understand that gravity can coupled with itself?
How does gravity couple with itself? Hello. What the question was?
Yeah, sir.
How does gravity couple with itself? Yeah, because actually, uh, uh, gravity, just like in electromagnetic magnetism, anything which has a charge is the source for electric and magnetic fields. In Einstein's theory of gravity, anything which has energy or momentum is the source for creating a gravitational field. So now everything in some sense has energy and momentum. So, of course, if something is moving, even light has energy and momentum. This is why light bends. When in general relativity, you think of light bending. But when space-time itself curves, that also needs energy and momentum to curve. Just like to bend a rubber sheet, you need to put in some energy. So curved space-time carries some energy, and therefore that energy will be a source for the gravity, which will be then also a source for more energy. So it is a coupled equation. You see, unlike in electromagnetism, the electric field and the magnetic field themselves do not carry any charge. Whereas here, the gravitational field carries the charge, namely energy and momentum, which is the source for gravity itself. So they kind of feed back on each other. So the curved space leads to energy, which then curves the space more, which leads to more energy, you have to kind of, that's why what is called a nonlinear equation. And you say that therefore gravity couples to itself. Gravity is a kind of non-linearly interacting force.
Okay, sir. Sir, there is a question by Mr. Sorkar. I think you can see the questions.
Why is c square used in this thing if the escape velocity? So there is no, c comes in as the speed of light, which is present in the Einstein equations, and therefore any solution of the Einstein equations, the speed of light enters as a in the Einstein equations themselves, just like in Maxwell's equations also the speed of light enters. And ultimately the reason is because gravitational signals propagate with the speed of light, the same as electromagnetic waves. Both are traveling at the same speed. Because they correspond to massless particles in the quantum theory. So C enters into Einstein's equations, and that's why it appears in the Schwarzschild solution and the Schwarzschild radius. But that should not be thought of as an escape velocity, because nothing can travel faster than the speed of light, and therefore if you're behind the horizon, yes, you are there, and light cannot escape, or anything else cannot escape, at least classically.
Okay, sir. Seema, I think you have another question, so you told earlier, so you can ask about it.
Yeah, so another question from Arijit Shi. He is from Life, and he wants to know that why do you choose to label string theory as conservative?
Conservatively, yeah. I was just saying that string theory is a modification of the framework of quantum field theory. So in that sense, there is a radical modification, but it doesn't modify too much, meaning it doesn't change the underlying rules of quantum mechanics. Everything is still built on the rules of quantum mechanics are unchanged. But it is just the framework which is changed, that instead of describing in terms of point-like particles and fields, you are describing in terms of extended objects, these strings. And so the mathematical framework is slightly more general, but it is ultimately, it is enlarging the scope of quantum field theories, but it is not overthrowing it completely. I mean, it is expanding it in some ways. So that's very unlike, say, Einstein's theory, which was completely had a different framework from the Newton's theory of gravity. So that's why that balance is what I was trying to capture in saying conservatively radical.
Sir, I have another question. We have lectures of Professor Supratik earlier about the dark matter and anything. So I want to know that you know that in recent times there is many proposal that dark matter and the dark energy is the fifth fundamental force or anything. That kind of proposals are in the magazines and science magazines also. So how do you? I want to know that is there any kind of quantum speculation of dark matter or anything?
Dark matter, yes, there are many proposals for dark matter. At one point, people thought these were what are called super partners due to a symmetry called supersymmetry, and they were hopeful of finding that in the collider, the Large Hadron Collider, but somehow that has not happened. But right now, I think amongst most physicists, probably the leading candidate for dark matter is something called axions, which are another set of particles that we believe must be there. So people think that maybe these are dark matter can be explained by axions. There are several other proposals also, including maybe some more exotic forces and so on. But I think there are many experiments underway, both not only in terms of colliders, but cosmologically also to understand dark matter and its interactions better. So hopefully in the next decade, we'll understand what exactly constitutes dark matter. But right now, the picture is still not clear. What are the other contemporaries of string theory and possible candidate for quantum gravity? Yeah, many people have tried to, of course, propose many theories for quantum gravity in the past also. I mean, starting from, I don't know, from Feynman onwards, many of them suffer from different problems or issues. I think there are several others, like there is this proposal of loop quantum gravity, which tries to quantize the Einstein's metric in a particular choice of variables. And there are other things like causal set theories and so on. There are spin networks and so on. But I think it is fair to say that none of them have come up with anything which is very compelling as a theoretical description. All of these descriptions, including string theory, are theoretical descriptions. But I think string theory's picture of quantum gravity, especially after this ADS-CFT correspondence, has a compelling nature because it connects with many other things that we know. And that's what gives it sort of a very natural, that this is really on the right track in describing quantum gravity. Yeah, I think I was just mentioning we don't still have the full answer. It is not from the bending of space-time that dark matter is created. The dark matter, of course, is about 4 to 5% of the matter in the universe. The matter content of the energy and matter content of the universe, and that of course is important for the large scale evolution of the universe, but it is not created by at least as far as we know, it's not created by the curved space itself.
Sir, I have a question. The question is asked by my friend. He is not able to attend due to network problem. So he is asking that as a researcher, if some physicist or some student is trying to insert in that quest of finding quantum spacetime, so what are the major challenges the physicists are facing nowadays in this quest of quantum spacetime? You are a professor and you are working on that field. So I want to know that what are the major problems the physicists are trying to solve in nowadays in this quantum spacetime, the quest of quantum spacetime?
Yeah, so these are some of the questions that I was leaving you with, namely, so we seem to have, at least in string theory, a string theoretic approach to quantum gravity. We seem to have a class of examples where we have a coherent proposal for what is quantum gravity. I think one is to decode that holographic picture in quantum gravity. I think that will teach us more about what is quantum gravity, at least in this class of examples. And then we can generalize it to quantum gravity in more general examples like flat space, asymptotically flat space as it is called, or even for the case which is relevant for our expanding universe, namely the so-called de Sitter spacetime or accelerated universe spacetime with dark energy. So in all these things, some basic important questions which we still don't understand are about still resolving the singularities of space-time, which I mentioned in the beginning of the talk, that Einstein's equations have. How exactly string theory resolves many of these spacetimes, or any quantum theory of gravity resolves these singularities, that I think is a very important question we have to understand. So these are some of the, I think, the most pressing challenges.
Okay, Seema, you have any questions to ask?
Yeah, I have one question. So that is why is string theory? That means I can just ask that there is a different method to understand quantum gravity, and one of them is string theory, and the other two have already that is loop quantum gravity and non-commutative geometry maybe. So why is string theory so important? That is my question.
Yeah, so I would say it is because it also allows you to connect with many other things. Most of these other theories, they are just focused on gravity and trying to understand how to quantize gravity as it stands. And I think their picture of quantizing gravity is a little too simple-minded. They kind of just change it in a simple, in some basic way, and that you can see in many of the problems they encounter. But I think in string theory, the idea of string-like excitations is telling us that you need to describe nature not only by point-like particles, which are the simplest. Maybe they are successful when you're considering ordinary quantum field theories, which are local, but gravity is in some sense a little more non-local. And of course, this idea of non-locality is what things like non-commutative geometry, even loop quantum gravity, they try to capture the idea of this non-locality that gravity has. but string theory captures it in a specific way in terms of extended objects. So they are not point-like and therefore not local in their interactions. And I think, therefore, string theory, I feel at least that that generalization of non-locality is the more fruitful one, because it also arises in a number of other contexts in strongly interacting systems, in gauge theories like that describing the strong interactions, like what is called QCD. There also you have string-like picture emerging. So I think the notion of string-like excitations in nature is very not a very uncommon one, and I think when we try to really expand our understanding of interactions, we I think will be forced to include string-like excitations also, extended excitations, not just point particle-like excitations. And string theory in some ways is a theory of extended objects. So that's one reason. I think it gives a consistent way to describe extended objects. So that I think is very much at the heart of string theory, and why it is perhaps successful in capturing some of the aspects of quantum gravity. So there's a question here about, is there any condition where quantum mechanics fails? Well, so far, at least, we have not seen any experimental situation or even any theoretical situation where we have good reason to think that quantum mechanics may fail. But of course, that doesn't, just because we haven't thought of it or found it in an experiment, doesn't mean that it doesn't exist. But it is just something we don't, as of now, we don't have any clue as to a situation where quantum mechanics might fail. So it seems to be the most robust system we have for describing nature, and it is probably likely to remain like that for some time. Of course, there can always be surprises.
So one last question from my side. I have studied a little bit about these kind of things. So obviously there is a lot of problem to understand all the things. So I want to know that there is a thing that is called p-branes. I think you should know about that. P-branes.
Yeah.
So I want to know that how that p-brane structure helps to study the quantum fluctuation of string-like behaviors in string theory.
Yeah.
So what's the basic concept about p-branes?
Yeah, so when I mentioned in my reply to the previous question that string theory actually captures extended objects very consistently, these D-branes are one of those extended objects. D-branes are P-branes in their original incarnation, but the P-branes refer to the generalization of membrane. A membrane is, you have a point particle, then you have a string, then you have a membrane. That's a two-dimensional extended object. Then you can have three-dimensional extended objects, especially if you're in higher space-time dimension. So these are called, now in string theory, they arise as what are called Dirichlet branes or D-branes. They are at some level, they are extended objects on which the endpoints of strings can end. So strings can come in two varieties: closed strings, which are like rubber bands, or open strings, which are like pieces of thread with two endpoints. And when you have open strings, the endpoints can you can give boundary conditions. You have to specify boundary conditions on the endpoints of the string. And one natural set of boundary conditions is that they end on some two-dimensional, three-dimensional, one-dimensional, zero-dimensional sort of surfaces. And these different kinds of objects have a consistent description in string theory, because you can talk about the strings moving on these very using the rules and recipes of string theory. And that means that you have So you can, that's why you can consistently describe these, and in some sense they're kind of forced on you in the theory. So you need to include them, and they are very important for many things like understanding the microstructure of black holes, etc. So yeah, that is more technical, but string theory now incorporates very naturally all these different p-branes.
Okay, sir. So I think we don't have much questions, and we will ask you in the mail if you have any questions and any queries. So thanks a lot for your precious lecture, and we hope you will also join us in future times. And thank you very much for your response. Thank you very much. I think we are going to end our broadcast. Thank you.
And bye-bye.
Okay, sir. Thank you. Have a nice day.
You too.